Welcome to the Lesson 34 demo. Today we're going to use all of our knowledge of functions to build mathematical models for real-world data. We're going to now be able to do that with exponential, log, and logistic models to our toolbox, which already included linear and polynomial models. So we've worked with graphs of each of these functions, but today we're going to build models based on real-world phenomena. So let's review the functions we've worked with so far, examine their key characteristics, and this will help us decide on the type of function to use as our model. So we use the shape of the scatter plot to help us choose a type of function. So linear functions, all the points sort of fall in a line or near a line. Quadratic functions, the points look like they form a parabola. Cubic, you'd have to have one arm up, one arm down, no more than two extrema. Quartic, it would be both arms up or both arms down, no more than three extrema. If you have more than three extrema, you got to go up a degree. Exponential is very fast growth. Logarithmic is slow growth. And logistic is the S-shaped curve. So if we want to build a model from data, data modeled with exponential and log functions are either always increasing or always decreasing. So let's take a look at some scatter plots of real data, help us make this determination. So I'm going to look at a logarithmic regression for some data. So I've got some data here for year and life expectancy of Americans from 1900 to 2010. So we're going to let X represent the year, represent the time in decades. So 1 is going to represent decade 1 from 1900 to 1910, 2 for 1910, and so on. So Y will represent the corresponding life expectancy, and we're going to use log regression to fit a model to these data. So the directions in here are going to use a graphing calculator to walk you through how to do this. I'm going to do it in GeoGebra since I'm at a computer, and it's a little nicer. You're not going to be asked to perform any kind of regression on any quiz or test or the final, but you will be asked to analyze a regression model that's given to you by using it to make predictions, by talking about whether it's a good fit or not. So the actual technicalities of how to produce this formula aren't going to be super important. So you can use a graphing calculator or GeoGebra for today. So for GeoGebra, I opened it up and I got the spreadsheet view up. If you don't have a spreadsheet view, you just go to View, choose Spreadsheet, hit it, do it again, get it back. Enter your data in the A and B columns. So in the A column, I entered all my data for years, 1 through 12. Those are actually decades, 1900, 1910, 1920, and then the life expectancy next to it. So if I want to create a scatter plot in GeoGebra, I'm just going to highlight all of this data, right-click, and choose Create List of Points. And there's all my points. I don't find it very helpful to have them labeled, so I think I'm going to select all of these and turn the labels off. All right, so there's my scatter plot. It does look like it's sort of logarithmic in that it kind of bends down a little bit as you move to the right. So this is just a picture of what I got in GeoGebra here. So I'm going to use the log regression command in GeoGebra. In your calculator, it's called lnreg, but in GeoGebra, it is called fitlog. Fitlog. And then you just have to tell it what list of points. So our list of points is named L1. So I do L_1. And there's my logarithmic regression. Looks like a pretty decent fit for the data. And I'm just going to move this over so you can see the whole formula is 42.53 plus 13.86 ln x. So that's what I've got here. I just included a lot more decimal places when I wrote it down. So graphing the model in the same window as the scatter plot, we've already got that done. It looks like a pretty decent fit. And we want to use the model to predict the average life expectancy in the year 2030. So that would be x equals 14. So to plug that in, my function in GeoGebra is f of x. So I could just do f of 14, and it gives me the number 79.1. So I just do f of 14 is approximately 79.1. So that was the age, 79.1 years would be the life expectancy in 2030. So if life expectancy continues to grow logarithmically, the average life expectancy of an American will be 79.1 by the year 2030. So here's another scatter plot where I have the results of the log regression that we just did and the linear regression, which also looks like a pretty decent fit. They both have an r squared value of 0.956, and the closer r squared is to 1, the better the fit. So how would we determine which model to use? We read the next page. So here's some guidelines, some consideration when you're trying to find an accurate model. Construct a scatter plot. Try different types of functions and see which appear to fit better just by eyeballing it. The more data you have, the better. Compare the scatter plot of the data with features of the basic functions. So our calculators give an equation for the curve of best fit, and they also give the square of the correlation coefficient. So the closer r squared is to 1, the more closely the model approximates the data. However, more complex models, such as Cordic, will tend to have higher values of r squared, but may introduce artificial behavior. So in general, use the simplest model that fits the data reasonably well. So in GeoGebra, if you want the r square value in GeoGebra, so your calculator gives it to you automatically. In GeoGebra, you type in the input, you type r square, and then it asks you for the list of points, so it's L1, and then the function is f. That's our model. And it says our correlation coefficient is 0.96, very close to 1. It's a good fit. Okay, so however, the linear model is also about 0.96, which means that it's a simpler model. It's got the same r square value, so we might choose the linear model. So try to find a model that fits well, provides a realistic view of the end behavior. So that's an interesting question too, because life expectancy can't just keep going up and up and up and up and up and up and up at a constant rate. So end behavior might indicate that the log model is better because it does keep increasing, but by smaller and smaller amounts. So generally, using models to interpolate, which is to find values between your data points, is more accurate than using them to extrapolate, which is to find outside unknown values, like the life expectancy, way over here, 22 decades after 1900, there's now a big difference between what our two models predict. So our model might be really off. So I think this is a matter of reasoning, and there is no right or wrong answer about which model you would choose. I think I would go with the log model because of the end behavior issue. I do want to note again, I already said this, but you are not going to be asked to perform regression on your calculator or GeoGebra on the final exam. You will be asked to analyze the appropriateness of a given regression model, use it to make estimations and predictions.